We can turn that off, Tom. So Friday, the aim of the experiment was simple. We launched a projectile, and you're supposed to be able to work out some property of the projectile from what we saw, and all we're going to work out is how the height, maximum height reached. We can't do that for Brad's rockets because the last one took something like, yes,
90 minutes.
I did write it down. I think it was 4 minutes something. Now, that's, if you do that roughly in your head, that means it reached an altitude of, I think it was over 100 kilometres. Obviously, gravity was not the only thing influencing it on the way downwards. So for the formulas that we've been using, the V equals U plus AT, which I assume is going to appear in a minute. There it is.
So why did this time how long did it do it reach at 8?
I'll tell you what in a minute. If you use these formulas here, right, they all assume one thing. They all assume that there's a constant acceleration and it's a known constant acceleration. Now, we use it here on Earth that A is equal to G, the acceleration due to gravity locally, which is 9.8 meters per second squared, right? But obviously, when both of Brad's rockets came down, spectacularly, one had streamers on it, which introduced air resistance into the picture, and the other one had a parachute, which also introduced air resistance, but because it failed and it was had rotational mechanics going in it, that alters everything.
Usually does that.
You could work it out, but we can't. We don't have the mathematical skill or background to do that. So we can only do the air rockets. The reason, Tom, we didn't do from launch, right, is because by the time you realised it was going up and pressed the stopwatch button, the acceleration that thing had, it would have been, 30, 40 metres off the ground by the time you started timing. And timing when it stops is much more difficult than starting your timing from when it stops. So we had the air rocket. As you know, it went up a certain height. It stopped there. That was when Vy equals 0, and then it fell. And we timed that time of falling from its maximum height to when it hit the ground. And that makes a task for us relatively easy because if we start our motion from this point up here, that means our Uy vertically equals 0. We know Ay, because it's in the same direction as the velocity, is 9.8 meters a second squared. And we measured the time for the various things we did. And therefore we can just choose one of our equations, which happens to be this one. The reason I use that is I want to know its height. I know Uy, I've timed T, and I know Ay, so I know everything I need. That's really easy. I can just substitute in. So for example, the first one we timed at, no, I'll go for the latter one, 5.2 seconds is one of the times we had. So if T equals, if time equals 5.2, then delta Y is going to equal 5.2 seconds. Because Uy is 0, you end up with 0 times T, which means the first term is just 0, it doesn't matter, plus 1/2 times the time, which was 5.2, no it's not, times G, 9.8 times the time squared, whoops. And if we put all that into a calculator, and I do have a calculator somewhere. I don't have a calculator there. Yeah, if someone can just plug that into the calculator. Yes, please. Just throw me a calculator. Oh, don't throw it at me. Just,
Step up.
so I'll drop it.
You better.
Tom. So 0.5 times 9.8 times 5.2 squared gives me an answer of 132.49 metres as the altitude for that one. Okay, so the calculation is really simple. And that's why we do it.
So that parachute was falling as well. So.
That was the air rocket.
That's the air rocket.
Oh, that was when you pumped up.
Yes, that's when I pumped up. Or everyone else pumped up.
How hard were the elements for?
The chemical ones, I'm thinking they were getting upwards of 700 metres probably. What would they have been, Brad?
You know how you just worked it out and then so you did half of it? So you didn't go going up, you went going down, and you do it with the other one going up.
Well, as I said, the problem is if you had an electronic timer, so that as soon as it lifted off the launch pad, you could then time it. But the other thing that you don't have is you don't know what your acceleration is. You'd have to then.
You just look up the rocket engines.
You could look up the rocket engine stats. That's one way of getting over it. Or the other way would be to use a slave mode with a ruler behind it, like they do on Mythbusters, and you can actually work out the acceleration that way if you wanted to. But it's more complicated than the air rocket and just watching it fall. So your results. What I'm going to do is I'm going to put trial run. You need to copy these down because you need them. Yes, I am. This is just in the back of your books or somewhere, so you all have results you can work on this afternoon. Okay. Now, I'm going to put down 1A, 1B because I have 2 times for the same one. Or I might have, oops.
That's a pretty.
And that was with the,
Where am I writing this?
just on a scrap piece of paper. So this afternoon when you write the prac report up, you have all the data for it. So that was with the white disc in it.
Was this one for the air pump, sir?
That does say trail, doesn't it?
Trial, should say.
That's like the only. Yeah, there we go.
What's the value?
So what's the W stand? What's grading it, sir?
That's the white disc. White disc and red disc.
You gotta go home and watch Chris tonight. What about A? Air rocket. Is that what it says?
A,
Yeah.
that just means if I have 2 times for each launch, I'll put A and B. So I only got 1 time for that one. Only got 1 time. This one I got 2 times.
Just quickly.
Yep.
It's got a statistics in the engine. C65, which is the most powerful engine of that size.
Yep.
Altitude range, depending on the rocket size, can be anywhere from 350 meters to 1,500 meters.
Okay. So I'm guessing 700
Pretty broad.
is very broad. That would depend on all sorts of things.
Yeah.